the Klein's group, which is an example of a finite commutative group, as well as example of a finite cyclic group. And first we will know the Klein's group and the different properties of Klein's group, and then we will solve some problem related to this important concept. So first we will define Klein's group. So what is the definition? Here definition is a group of order 4 of order 4 in which in which every element is self inverse is self inverse is called Klein's group is called Klein's group, and it is denoted by K4, or in some book you will see V4. And here the important note, who is Klein? So Klein is basically the German mathematician, name is V. Klein, was a German mathematician and V comes from the German word Vargruphi. Okay, so now we can define in alternative way, that is another definition of Klein's group. So this we can consider the definition 1. We can define in other way. K4, a group generated by two elements, a group generated by two elements K4 equals to, it is generated by two elements A comma B, such that A square equals to B square equals to AB whole square equals to E is the identity, is called Klein's group. And here another important note is order of K4, or you can write in that way, mod of K4, as this contains 4 elements. So here order is 4. And this we can write 2 square. So this is an example of not 2, not 3. K4 is an example of a commutative group as well as cyclic group, as well as a cyclic group of order p square, where p equals to 2 are prime. Now here we will show that how it basically forms a group. So that is justified. Here the question is so Klein's group, we'll see that this group is an abelian group. So here important note is correct or justify K4 Klein's group. Klein's group K4 is an abelian group. Is an abelian group. This is basically question number 21, and that question asked in Calcutta University B.Sc examination. So how we will show the Klein's group is commutative. So let K4 equals to EABC and not be a binary composition, be a binary composition on G, or you can say on K4 as follows. So this is E composed A, this equals to A composed E equals to A. E composed B equals to B composed E equals to B. And E composed C equals to C composed E equals to C. And A composed A equals to B composed B equals to C composed C equals to E. And A naught B equals to B naught A equals to C. B naught C equals to C naught B equals to A. And A naught C equals to C naught A equals to B. So here the binary composition is defined as follows. Then what should be the composition table? Then the composition table is so here we'll draw the composition table, not operation EABC. Here also EABC. E composed E, this is E. E composed A is A. E composed B is B. E composed A is C. A composed A is A. B composed A is B. C composed A is C, which is exactly given here. Okay, and A composed A, here you will see A composed A is ident E. B composed B is also E. C composed C is also E. And A composed B is C. A composed C is B. B composed A is C. B composed C is A. C composed A is B. C composed B is A. So this is our composition table according to the binary composition. So then it appears from the table G is closed under not. Here we will see in the composition table all the elements belongs to E, A, B, C. So what we will write here, it appears from the composition table that G is closed under the binary composition not. And second, you will see here clearly not is associative on G. Clearly here you just consider G equals to K4. So clearly not is associative on G. And next you will see from that line, from these three condition is the identity element. So it is clear. So here you just consider the principal diagonal and you will see E is left identity, and from that column you will see is the right identity. So we can see from the table clearly E is the left as well as the right identity. So is the identity element in G. And fourth, I will check it is existence of inverse, because to be a group it holds closure, associative, identity, inverse, all the property. So now we will just see the principal diagonal. We will check. So E composed E is E, A composed A is E, B composed B is also E, and C composed C is also E. Okay, so from that you can conclude the inverse of each element is itself. So clearly from table, the inverse of composition table, we can say the inverse of EABC are also EABC respectively. Okay, so that means closure associative existence of identity inverse all holds. So therefore, G is a group. G is a group with respect to the given composition, not. So G means here Q4. Q4 equals to G is a group. Again, if we see the principal diagonal and the table is symmetric with respect to principal diagonal, here you will see A. So just you fold the table with respect to principal diagonal. What you observe? So here observe, you will fold it with respect to principal diagonal A, and B is C in that position, CC, BB, and A. So that means what we have seen the commutativity property is also hold. So since the table is symmetric, since the table composition table is symmetric with respect to principal diagonal, so the K4, that means G is commutative with respect to composition, given composition. So what we have proved here, we proved here K4 is an abelian group with respect to composition. Okay, and also this is our observation. What is our observation? Here number of elements in K4, this is equals to 4. That implies order of K4 equals to 4. And this is of finite order. Okay. So now there are some properties of K4. Properties of Klein's 4 group. That means K4. So what are the properties? The properties is all non-identity element of the K4 have order 2. So property 1, all non-identity elements of K4 Klein's 4 group have order 2. Because we have seen order of A equals to order of B equals to order of C equals to 2, and they are the non-identity element. And here the second property, so it is also the every element of K4 is its own inverse. So you may have asked this kind of questions. Give an example of a group. You ask the question. The question is 22. CH. Give an example of a group in which every element is its own inverse. Every element is its own inverse. Okay, so this is for 2 marks. So we have the solution planes for group. Planes for group. Q4 is the example where you will see every element. Since inverse of E is E, inverse of A is A, inverse of B is B, and inverse of C is also C. So here every element is its own inverse. And you have also asked the question number 23. So give an example of a group which is commutative. Give an example of a group which is abelian but not cyclic. So again here the example is, this is for 2 marks question. Again Klein's for group. Klein's for group. That means K4 is an example. Okay. So we'll check here K4 is an abelian group, and it is our observation. Our observation that does not exist any x belongs to K4 such that order of x equals to 4. Because we already know the order of A equals to order of B equals to order of C. That element order is 2. And order of the identity element, this is 1 in K4. K4 means E, A, B, C. So that means there does not exist an element x belongs to K4 such that order of x equals to 4 equals to order of K4. And hence we can conclude K4 is not a cyclic group. Cyclic group, as we know, recall a group G is called cyclic group if and only if there exists an element x belongs to G such that order of x equals to order of G. Okay, and this is not happening here. So K4 is not a cyclic, but okay, you will check clearly K4 is a commutative group. But it is not a cyclic. So this is an example of a commutative group which is not cyclic. Okay, you may ask this kind of question. Question number 24. Give an example of a group whose order is the prime square. Okay. So again the solution is K4, because since order of K4 equals to 2 square, and that we can write P square where P equals to 2 is a prime. Okay, and here important observation, or you can say the recall, this is the smallest non-cyclic group. So K4 is the smallest non-cyclic group. Okay, however it is abelian, but okay, it is smallest non-cyclic group. And again you may ask this kind of question in CU, Calcutta University, Calcutta Honors Examination. Give an example of a non-cyclic group. Give an example of a non-cyclic group whose every proper subgroup is cyclic. Whose every proper subgroup is cyclic. Again, our answer is Klein's for group. Klein's for group. This is an example. This is non-cyclic group. Non-cyclic group. K4 is non-cyclic. Okay, because since there does not exist any x belongs to K4, such that order of x equals to order of K4, that means 4. So that set is not cyclic. And you will see here, the second observation you will check, every proper subgroup of K4 is cyclic. Okay. So these are the few questions you have asked in examination. Okay. And it is also an example of a finite commutative group. Thank you so much.